Section 8.2 is all about the good old Pythagorean theorem and the converse of the Pythagorean theorem. So our goals today, the Pythagorean theorem is always used to find missing side lengths of right triangles. And the converse is used to determine whether triangles are right, acute, or obtuse. So make sure you get this in your notes as section 8.2. So first, the Pythagorean theorem. As a conditional statement, in other words, as an if-then statement, the Pythagorean theorem says if you have a right triangle, then a squared plus b squared equals c squared. So a and b are called the legs, c is the hypotenuse of this right triangle. So for example, if we had 5, 12, and unknown, we would find that that unknown hypotenuse is 13. So once again, the two sides that are connected to the right angle are called the legs. The side opposite the right angle is always called the hypotenuse. Let's look at a couple of examples. Here we have a right triangle where the two legs are 40 and x, and the hypotenuse is given as 85. So Pythagorean theorem says x squared plus 40 squared is 85 squared. If you square both 40 and 85, you get that. If you subtract 16, we get that x squared equals 5625, and square rooting that gives us that x equals 75. And so that tells us that 40, 75, 85, since all three of those numbers are integers, that's a Pythagorean triple. So some other common Pythagorean triples, 3, 4, 5 is a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. Likewise, any multiples of 3, 4, 5 will be Pythagorean triples. So 6, 8, 10, 9, 12, 15. Some other Pythagorean triples, 5, 12, 13 is a Pythagorean triple, 8, 15, 17, and a bunch of others are Pythagorean triples. So another example here. Here we have x is the unknown hypotenuse, and so, oh wait a minute, leg squared plus leg squared equals hypotenuse squared. So we have 6 squared plus 12 squared is x squared. So that means x is equal to the square root of 180, and 180, we can simplify that radical. 180 has 36 as a factor, and so x is equal to 6 root 5. Here's another example, a little bit more advanced example. We have two legs that are unknown. One is bigger than the other by 2 units, and so x squared plus x plus 2 squared is equal to 10 squared. Now remember, the quantity x plus 2 squared is equal to x plus 2 times itself. And so using the distributive property, x plus 2, the quantity squared, is x squared plus 4x plus 4. And so, back to our original equation, we have x squared plus 4x plus 4 equals 100. Combining the two x squareds and then subtracting 100, we have 2x squared plus 4x minus 96 equals 0. Now note that this trinomial has a greatest common factor, so we can factor out the 2, and then we have the trinomial x squared plus 2x plus, x squared plus 2x minus 48 factors to 2 times the quantity x plus 8 times the quantity x minus 6. And that equals 0. So the first term equals 0, x plus 8, or the second term, x minus 6, equals 0. And so we have these two algebraic answers, x equals negative 8 or x equals 6. However, x equals negative 8. If you substitute that value in for x, then we have a negative leg, a leg that is negative units long, which is ridiculous. It makes sense algebraically, but it doesn't make sense geometrically. And so our final answer should be x equals 6. Here's another example. Maybe try this on your own if you want to. Press pause and see how it works out for you. So we know leg squared plus leg squared is hypotenuse squared. So that means x squared plus 2x plus 1 plus x squared plus 6x plus 9 is equal to, now here we have the square of a square root. Those are opposites, and so we're left with what's underneath the radical symbol. Now if we go through and clean up the left side of the equation, we have 2x squared plus 8x plus 10 equals x squared plus 15x. I'll subtract x squared, and I'll subtract 15x from both sides of the equation to get a nice factorable trinomial. And then I'll factor that. I get x minus 5 times x minus 2 equals 0. So x is 5 or x is 2. Now if you take and substitute those values back into the original legs and hypotenuse, we see that both answers are okay. And so you don't pick. You actually report both answers as possible answers to this question. Now we come to the converse of the Pythagorean theorem. Remember, the original Pythagorean theorem said if we have a right triangle, then a squared plus b squared is c squared. The converse switches around the if-then statement. Now we say if a squared plus b squared equals c squared, then this is a right triangle. And so some bonus features of the converse: if a squared plus b squared is not equal to c squared, then we have some different types of triangles. In fact, if a squared plus b squared is bigger than c squared, then we have an acute triangle. It's worth noting that a and b are always the two shorter sides of the triangle. C is always the largest side, or the longest side. Similarly, if a squared plus b squared is less than c squared, then we have an obtuse triangle. So let's examine a couple of examples here. First, with these triangles, or with these potential triangles, you have to check whether it's a triangle or not, and if it is a triangle, we'll classify the triangle as right, acute, or obtuse. So potential side lengths, here we have 16, 12, and 20. First, is it a triangle? Well, it's a triangle because the sum of the two shorter sides is greater than the third side. If you remember back to chapter 5, that indicates whether we have a triangle or not. So since it's a triangle, we want to check to see what type of triangle it is. So we'll look at 12 squared plus 16 squared. How is that related to 20 squared? Well, 12 squared and 16 squared, that's 144 plus 256, which is 400. 20 squared is also 400. So therefore, a squared plus b squared equals c squared. And so that means we have a right triangle. We have also found another Pythagorean triple, 12, 16, 20. How about another example? New side lengths, we have 4, 2, and 3. First, does it make a triangle? Yes, indeed. The two shorter sides added together is greater than the third side. Now, what type of triangle is it? Well, we know 2 squared plus 3 squared. Well, that's 13. And 13 is less than 16. So, since a squared plus b squared is less than c squared, we know we have an obtuse triangle. How about these side lengths? 5, 6, and 4. Give it a try on your own. Pause the video and check to see whether the triangle exists, and if it exists, classify it as a right, acute, or obtuse. We know this does exist because 4 plus 5 is greater than 6, so therefore this is a triangle. And we also know, since 41 is greater than 36, this is an acute triangle. This example, 13, 34, and 21, it's not even a triangle. Because the sum of the first two sides, sorry, the sum of the two shorter sides is equal to 34 and not greater than 34. So therefore, we have to stop at part A. We don't have a triangle, and so therefore it can't be right, acute, or obtuse. We have one more example here. Let's say we have a rectangle, and it's 8 inches tall. It has a diagonal of 12 inches long. How wide is the rectangle? Well, even though we're dealing with rectangles, this question is actually a question about triangles. We know that because its diagonal is given. The diagonal is 12, the height is 8, rectangles have 90-degree angles, and so we can solve this using the Pythagorean theorem. So we have x squared is equal to 4 square roots of 5, and so the width is 4 root 5 inches.